It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good afternoon, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we are going to talk about diffraction. We're finally going to settle the debate between Isaac Newton and Robert Hooke in terms of whether or not light behaves like a particle, which is what Newton said, or if light behaves like a wave, which is what Hooke said. Hopefully by the end of this video you'll have a greater understanding of the behavior of light. However, you might be more confused about how light actually behaves. So you have a deeper understanding, but that understanding might be slightly confusing. If by chance you found this video enjoyable and want to learn more about it, one book you could read is called Through Two Doors at Once, the elegant experiment that captures the enigma of our quantum reality. And this talks about the double-slit experiment, which is what we're going to get into today. Much of these notes come from Feynman's lectures on physical law that he gave at Cornell. So, let's get started. We're going to use a couple of analogies to look at how light behaves as if it were a particle or a wave. So the first analogy we're going to use is treat light like a particle or NERFs. So here's our NERF gun, we'll call it our source. Let's say it has 100 rounds of NERFs in it. And somebody's going to shoot those NERFs through a single slit and a protective barrier on our wall. Once those NERFs go through that single slit, we're going to have another set of slits called our double slits, hence the name the Double-Slit Experiment, where the NERFs can now either go through, let's say, hole 1 or hole 2. And then they're going to land on the other side of a wall that's going to capture all those NERFs. And what we could do is, since we know that since they're NERFs, they're going to hit this wall, we could count how many land in each spot. Now we have to come up with a few constraints for this analogy. Number one is that we're going to say that the NERFs go either through hole 1 or hole 2. We'll also say that the NERFs are indestructible, so we can't have half a NERF landing on the wall. It has to come in whole amounts, so 1, 2, 3, or 4 amounts of NERFs. So let's write down what it would look like if we treat light as a NERF. So the first thing, we'll put down our constraints. Number one is that the NERFs are indestructible. So they have to come in whole numbers, which means we'll say that they come in lumps. And since they come in lumps or whole numbers, that means we can count how many NERFs hit the wall. So we can count the number of lumps. So what we could do is we can draw a graph or a picture of what it would look like if we counted all the NERFs that hit each spot along the wall and make a plot of all of those NERFs. If we were to do that, we're going to get the most amount of NERFs that go around or in the center of hole 1, or in the center of our first hole, our first slit. So if we drew a plot, we're going to get the maximum amount of numbers. Let's redraw that. Look at the maximum amount right in the middle of our first slit. So we're going to call this N12. That's the number of nerfs that went through hole 1 and hole 2. Now if we perform this experiment hundreds or thousands of times, we're going to get a very similar picture, and that means that we can measure the probability of arrival. So we could predict where the nerfs will land if we do this hundreds or thousands of times. So measures probability of arrival. So this is what it would look like if we treated light as if it were a particle, or in this case, a nerf. Now we could add to this experiment. So we're going to draw another wall. And this is going to be the same thing as our last wall where the nerfs hit. We're just going to look at a different scenario. So in this case, we're going to close off hole number 2 and just keep hole 1 opened and count the number of nerfs that hit the wall when we keep hole 1 opened. If we do that, we're going to get a picture something like this, where we get a lot of nerfs right in the middle of hole 1, and then we're going to get less and less the farther away we get. And we can call this the number of nerfs that go through hole number 1, or N1. We can do the same thing but the opposites. This time we'll close hole number 1 and count the number of nerfs that go through hole number 2, and we'll get a similar picture. But again, it'll show us the number of nerfs that go through hole number 2, which we'll call N2. Now if we take the number of nerfs that went through just hole 1 while hole 2 was closed, and the number of nerfs that went through hole 2 while hole 1 was closed, we add these up and we get N12. So the number of nerfs that went through hole 1, we'll call this, number 5. The number of nerfs that went through hole 1 plus the number of nerfs that went through hole 2 is equal to the number that went through holes 1 and 2 when they were both opened. So the reason why this works is because there's no interference between the nerfs. Meaning that there's no constructive interference or destructive interference, whether or not we have just hole 1 opened, just hole 2 opened, or both of the holes opened. So if we treated light as if it were a particle or a nerf, this is what we'd get. This is behavior we'd see. Next, let's treat light as if it were a wave, like what Robert Hooke said. To give you a better image of what it looks like, I'm going to have my hand model show you what water waves look like when they interfere with each other. Oh, hi. Didn't think you'd see me here. How's it going? Mr. Tibbetts kicked me out of the house since the quarantine, being a germaphobe and all, so I've been living out here in the woods, but I guess I'll make one more video for us. What we're going to look at here are interference patterns of water waves. So we want to focus on constructive interference, where the waves combine and the amplitude increases, and destructive interference, where the waves combine and the amplitude decreases. So let's take a look. Hopefully my hand model was able to make waves with only 9 fingers, and I hope you're able to see the periods of constructive and destructive interference. Let's draw a picture of what happened just in case. So the source of water waves, in this case just from one raft we could say, making waves in a pool, are equally distanced, so they have the same wavelengths. They go through the first slit, so now they'll be rounded off. Again, same wavelengths, or as best as you can to get equal wavelengths. And then they go through hole 1 and hole 2. So this is the image that you saw of my hand model. So let's draw wave fronts going out of hole 1. Eventually they're going to hit the wall. And let's draw the wave fronts going out of hole 2. And we can see that there's periods of constructive and destructive interference between these two waves. Now when the waves, the red wave and the purple wave, when they interfere at the same spots, we're going to get periods of constructive interference. So if they intersect and they're at the same aspects of the waves, that means we have a crest and a crest. If they interfere and we have different aspects, so for instance, if we look at the first purple wave and the second red wave, we're going to have destructive interference because they're at different spots. So, rather than counting the number of waves that hit this wall, what we're going to do is measure the intensity of the waves. So what's their amplitude, or how strong are they? So for waves, the first thing we could say is that we're measuring the intensity. And what we can do is make another screen. So we'll look at the wall that the waves hit. We're going to draw it farther to the right. And as we can see, is that we're going to get maximum constructive interference right in the middle of the source. And then we're going to get periods of destructive interference, constructive, destructive, and so on and so forth. So we'll draw our maximum constructive interference right in the middle of our first hole. That's where we're going to get the largest wave. And then destructive, a little bit of constructive, and so on and so forth. So if the farther away we get, the smaller the waves become. And we can do it on the other side towards hole 1 as well. And so on and so forth. So let's call this I12, the intensity of the waves that goes through holes 1 and holes 2. So just to be clear, when we treated light as if it were a nerf or a particle, we're counting the number of particles that hit the wall, that's N12. When we treat light as if it were a wave, we're measuring the intensity or the amplitude of the wave when it hits the wall. If we were to close hole number 2 and just keep hole 1 open and see what happens, we would get the same thing as N1. So we'd get the same image or same plot, although in this case we're measuring the intensity of the wave that went through hole 1. We could do the opposite, close hole 1 and open hole 2, and we get the same thing, the intensity of the wave that went just through hole 2. So although the images look the same, they mean two different things. N2 is the number of particles, I2 is the intensity of the wave. If we added these two together just like the particles, we don't get N12. So we can say that I1 plus I2, measuring those two intensities, does not give us N12. The reason being is because it shows constructive, or shows interference, constructive or destructive. So shows interference. And again, that's because, as we saw, the wave fronts are going to interfere with each other. So if we have a crest and a crest, we'll get constructive interference. If we have a crest and a trough, we get destructive interference. And then farther out, the waves are going to get weaker, so we get less constructive interference. So let's see what happens when we treat light as if it were actually light. We can either treat light as if it were a photon or an electron. We'll get the exact same results. So we'll just treat it as if it were a photon, or a bundle of energy. Now what we can do is if we treat a light as if it were a photon, so let's say our source is a flashlight, and we're shooting one photon out at a time out of this flashlight. On the wall, we can have what's called a photomultiplier tube, and we'll have a whole bunch of them across every aspect of the wall. And the photon will go in the photomultiplier tube. We'll hear a click each time it hits that photomultiplier tube. So we're going to have a whole bunch of detectors along here, which means that we can count the light that hits that detector. Because we can count the light that hits the detector, we could say that photons, just like nerfs, come in lumps. Now if you turn on a flashlight, a whole bunch of photons are going to be emitted. So we have to do this in really super slow motion, so we hear one click at a time, or one photon at a time. Just like nerfs, because they come in lumps, we can also count the number of lumps. Which means that we can measure the probability of arrival. So if we counted all the photons that hit the wall, we could get a probability of how many are going to hit each spot along the wall. So since they behave just like nerfs, the image that we get when we measure the probability of, whoops, I spelled photon wrong. Sorry. P-H-O-T-O-N, not photon. Anyways, since we can count the number of photons that hit the wall, and we can measure the probability of arrival, the image that we'd expect to get is N12. However, something weird occurs, and the image we get is I12. So the probability of arrival that we get for photons is going to be I12, which means we get the maximum amount right in the middle, and then no photons, a little bit of photons, no photons, less, none, and so on. So rather than getting the expected results of N12, we're getting the unexpected results of I12. So the number of photons that we count is equal to I12. Now remember, N12 represents the number of nerfs that we counted. I12 first represented the intensity of the waves, but now it also represents the number of photons that we're counting. Which means that if we're getting I12, that the photons are interfering with each other. So this shows interference. So notice 1, 2, and 3, those are all properties of a particle. Both 4 and 5 are properties of waves due to interference. So if we did the same thing by closing off both holes, or one at a time, if we closed off hole number 2, we would get N1, which counts the number of photons that went through hole 1. If we closed off hole 1, we get N2, the number of photons that went through hole number 2. And if we counted the number of photons that went through hole number 1, the number of photons that went through hole number 2, we would expect to get this image of the number of photons going through holes 1 and 2, but the number of photons that go through holes 1 and 2 is I12. So we can say that the number of photons that go through hole 1 plus the number of photons that goes through hole number 2 does not equal N12. And I should have put this over here too under waves, it does not equal N12. And that's because there is interference. Now if we look at our picture, what's weird is that here we have the maximum constructive interference when holes 1 and 2 are opened. If we have just hole 2 opened, notice right here we have the maximum amount of photons. And if you look at what happens when both of them are opened, we have 0 photons. So for some reason, when light goes through just hole 1, 2, we get a lot of photons in this location. But when it has the option to go through hole 1 or hole 2, all of a sudden we get 0 photons. So somehow they're canceling each other out, showing us destructive interference. So maybe all of a sudden light says, well, if I have just hole 2 opened, I'll get a lot of photons in this location. But if I have hole 1 and hole 2 opened, maybe for some reason there aren't any photons going through hole 2 right here. Or maybe they're moving around in between and just deciding not to go right here because they can't cancel photons out. You can't have 1 photon plus 1 photon give us 0 photons. So something weird is going on when we have just 1 hole opened compared to both holes opened. So what we're going to do is set up an experiment to look at that weirdness. Now we know that the photon has to go through hole 1 or hole 2. So what we're going to do is shrink us, and we're going to have somebody stand by hole number 1, and somebody stand by hole number 2, and they're going to observe, if we shoot 1 photon at a time, they're going to observe what hole that photon went through. Now because it's going to be dark in here, we want a flashlight aimed at hole 2 and a flashlight aimed at hole 1. This way when that photon interacts with that light, it'll eject a photon that the person could see. So they'll know whether or not it went through hole 1 or hole 2. So we're going to shoot 1 photon at a time from the source. If it goes through hole 1, the person hole 1 is going to say, I saw it, and we'll hear a click. The next time, if we shoot a photon, we hear a click, either person 1 or person 2 saw it. So let's make a chart. Either the photon went through hole number 1, or it went through hole number 2. And each time, again, we'll hear a click, and the person, either 1 or 2, could say which hole it went through. Okay, so are we ready? Click. Hole 1 saw it. Click. Hole 1 saw it. Click. Hole 2 saw it. Click, click, click. 2, 1, 2, 2, 1. Click, click, click. 1, 2, 1. After we go through 100 clicks, we're going to count where each of the photon landed along the wall, and guess what image we get? Well, we should get I12 because that's what we get for photons, but in this case we get N12. So now all of a sudden, by observing where the photon went through, either hole 1 or hole 2, we get an entirely different outcome where a photon behaves just like a particle. We get N12. If we don't know where the photon went through, we get I12. So in other words, if we know which hole it went through, we don't get interference. If we don't know which hole it went through, we do get interference. So what we could do is say, well, maybe this light is interfering with the photon, so we'll dim our lights. So let's try the same experiment. We have somebody by hole 1 and somebody by hole 2, and our lights are dimmer. Okay, ready? Click. Hole 1. Click. 1. Click. 2. Click, click. 2, 2. Click. Hole 1, do you see it? Hole 2, did you see it? Interesting. This time, because they were so dim, nobody saw it. So I'll add a column under didn't see. Click. 1. Click, click, click. 2, 1. Didn't see. Click. Didn't see. We'll do this 100 times, and we'll count all the photons that hit the wall, and guess what picture we get? We get I12. So, when we know which hole the photon went through, we get N12. When we don't know which hole it went through, we get I12. And if we sometimes know if it went through hole 1 or hole 2 or didn't see, we also get I12. So what's happening here is when you know which hole the photon went through, we don't get destructive interference or constructive. When you don't know which hole the photon went through, we get an entirely different pattern which shows interference. Now, if we look at this book from earlier, through 2 doors at once, there's a ton of experiments in which scientists are tricking light into not knowing, into thinking that we don't know which hole it went through. And no matter what we do to trick light, if we know which hole it went through, we're always going to get N12, so no interference. But if we don't know which hole the light went through, we're always going to get I12. So by somehow knowing the path that light takes, we're now disturbing how it naturally behaves. And we always get interference patterns if we don't disturb the outcome. There's been a ton of experiments performed to determine the behavior of light in terms of, does light behave like a particle? Does light behave like a wave? Or is it a combination of a wave and a particle? And no matter what experiment we perform, if we don't know the direction that the light travels, we're always going to get I12. So because we can count the number of photons, we say it behaves like a particle. And because we get the intensity like a wave, we say it behaves like a wave. But in reality, it doesn't behave like a wave or a particle. It behaves like its own thing, like a photon. There's one theory called the pilot wave theory, and I'll attach a video on this in which light is a particle, but it's surrounded by a wave. Alright, so why don't we finally define diffraction? So all we're going to say with diffraction, in terms of for Regents physics, is that it's the double-slit experiment demonstrating that light behaves like both a particle and a wave. Now, even though technically it's neither a particle nor a wave, because it has characteristics of each, we're going to say that it behaves like both. Now, let's look at the double-slit experiment of actual light to see if we do get these different periods of constructive interference and destructive interference. Oh, dang it. Didn't think you'd be watching. Lifting these really heavy 5-pound weights. But I guess I'll set them down and we'll do some physics. So what we're going to look at is a double-slit experiment with a laser pen. So here we have a green laser pen. I'll shine it on the wall and we see a dot. And this here is our diffraction grating. And this is going to act like our double slit. So if we shine the laser through the double slit, hopefully what we see is what we expected from the video, that we get periods of constructive interference, where we see bright spots of light, and destructive interference, where we don't see any light. So let's see what happens. And as you can tell, I'll turn the lights off in a second, but as you can tell, it's very bright right here. No light right here, so it's complete destructive interference. And as we get farther out, it's going to get dimmer and dimmer. If you move it to the right, we can see it's going to continuously get dimmer. We do the same thing for violet light. It's hard to tell, but I think this is the brightest one. And then as we get farther away, no light, dimmer, no light, dimmer, and so on. We could look at them at the same time to see what's the difference between green and violet. So we'll turn the lights back off. You need them on to hear my voice. Sorry, it's difficult to aim. And if we get them, where's your bright one? That one? We can see, if we line them on top of each other, that the violet light is closer. The violet light is closer than the green light. And we'll talk about why in the video. Okay, good enough. Hopefully you were able to see that we saw the brightest green and violet light right in the middle. And then we got a spot of nothing, so destructive interference. And then a dimmer light, nothing, dimmer, and so on and so forth. So we get the brightness is measured by the amount of photons. So we got the most amount of photons right in the middle. No photons, less, no, none, less, and so on. Also, we saw that the violet lights, the periods of interference were closer together. So we got a whole bunch of violet in the middle, and then less blank space before we got to the next diffraction pattern. Now the reason being is because the violet light, its wavelength is more closer to the width of the slit. So the closer the wavelength is to the spacing between the hole, the more patterns we're going to get and the closer they'll be. So we can say, lastly, that the more similar the wavelength of light is, to the width of the openings or holes, we'll say the holes are the slits, the more bright spots we'll see, or the closer the bright spots will be. And we could say that means that there is more diffraction. Again, I know this video is probably a little bit confusing, but so is the behavior of light. Hopefully you have a better idea, again, of how light behaves. Not necessarily why it behaves this way, but just a better depiction of what it does in different scenarios. If you found this video useful, please like and subscribe, and I'll see you next time. See ya!